Before we begin, so each speaker has 30 minutes, including questions. You can divide that time however you want, but when you have 5 minutes left, I will stand up. And if you choose to keep going, then that'll just eat into your question time. And in 30 minutes, I will stop you, and then questions can, and then you can ask your questions later after the talk. Okay. So our first speaker this afternoon is Duncan Hanson. He did his PhD at Cambridge, and then a postdoc at Caltech in JPL, and he's now CITA National Fellow at McGill University, and his research gets related to the CMB spectrum. I'll let him speak.
Okay, well, Graham did a really good introduction in the last talk to CMB, but I love it so much I'm going to do it again. So this is the image that you will get if you look at the sky in microwave frequencies, sort of between 50 and 200 gigahertz. You remove galactic contamination. So you just look for something that looks like a thermal black body with a temperature of about 3 degrees. And this is what you see. You see this pattern of hot and cold spots distributed over the entire sky. And these are ripples at the sort of 10 to the minus 5 level of density and pressure in the early universe. If you take the power spectrum of these things, you get this famous WMAP plot. So this is from the first year of WMAP data. The black points are WMAP measurement of the power of these hot and cold spots as a function of angular scale. So it's the Fourier transform of the sky, and then you take its modulus and you put it on this plot as a function of scale. This is what you get. And these peaks correspond to breathing modes in the early universe of overdensities that were collapsing and expanding. You can see them wiggling all the way down. So WMAP really revolutionized this field. But you can sort of see from these points, which were pre-WMAP, that we already sort of knew what the power spectrum looked like. So while Graham did a great introduction of why the power spectrum is important and we should care about it, I'm going to try to convince you now that it's not as exciting as many of the other aspects of the CMB, which it so happens that I study. So here's the WMAP spectrum, the sort of fiducial one, plotted in a different y-axis. So the y-axis now is L to the 4th instead of L squared. That just brings out the small scale structures. And over the last couple years, the CMB power spectrum at higher angular scales than WMAP controlled with its sort of 15 arc minute beam have come from these, in particular from the ACT and SPT experiments. A lot of people here work on ACT. So if you add them to this spectrum, you go out to much smaller angular scales. The important thing is that this flat curve here, we already knew based on WMAP, and you could argue even pre-WMAP data, pretty much what it would look like. You knew the position and basically the relative height of these peaks. A lot of what we've learned about the CMB, or about a lot of the new stuff that we've learned from ACT and SPT is actually this stuff at very high L, which turns into foreground contributions that Graham showed. So the point here is that although it's really useful to measure these peaks with increasing precision, you're not going to discover a new peak, right? The discovery potential for the CMB in the power spectrum, at least, was achieved a long time ago. So we're at the stage now where we're doing precision cosmology. So we're measuring these peaks really, really accurately. And we're using them to nail down cosmological parameters. But you sort of have to remember that we're measuring like percent level cosmological parameters when there are bigger things that we don't understand, like what is dark matter and dark energy. That measuring the relative amplitudes of them to greater precision isn't necessarily going to help us at all. Planck is going to come out in a couple of weeks and really do as well as can possibly be done for all of these modes between 500 and 2,000 or so. So it's going to make a measurement with low enough noise that you couldn't do any better than you can with nature. Okay, so what I'm going to talk about is what you can learn apart from just a power spectrum. Because in fact, when we observe a CMB, we make a map. And the power spectrum is a kind of radical compression of all of the information in that map down to that one line. So there are two aspects of the CMB beyond the power spectrum at the statistical level. So the power spectrum is a two-point correlation function. It completely characterizes the statistics if they are Gaussian random variables. But if they're not, then there's a lot that you can learn from the higher order statistics of the CMB. So the bispectrum and the trispectrum. I don't know the names of any of the higher order polyspectra. Have numbers in front of them. Okay. The other thing that you can study is statistical anisotropy. So this is what happens if the CMB might be Gaussian, for example, but the amplitude of the fluctuations, so the power spectrum of the fluctuations, or there's a preferred direction of the fluctuations which varies as a function of position on the dial. So in both of those cases, you don't look at the power spectrum, you look at the ALMs themselves. So this is an example of a power spectrum, or of a representation of the CMB which is statistically anisotropic. So if you take a map, you decompose it into these Fourier modes. You take the modulus of the different Fourier modes, but then instead of averaging them over the azimuthal quantum number, you just plot that around this circle. Normally we assume that the CMB is isotropic all the way around this circle, but you can have dependences of the power spectrum on position on the sky, which shows up in the plot. So there's an elegant framework for studying both of these things, which actually goes back to power spectrum estimators themselves, and it's sort of first proposed, I think, by Dick Bond. I don't know if he's here, but I'm sure that if you ask Dick, he'll have a slide somewhere with everything that you need to know written on it. Just one slide. Just one slide. I'm not really going to talk about the math that goes into estimating these things in this talk. I'll try to give more intuitive pictures of how this all works. But this framework is really nice. Okay, so here's an outline. I sort of cut my teeth with this stuff using WMAP data. So I'm going to talk about that in the first part of the talk, where I talk about looking for evidence of new physics in the CMB. And then in the second part of the talk, I'm going to talk more about high-resolution data that we have from Planck and ACT and SPT that we can actually use to constrain non-Gaussian or statistically anisotropic effects that we expect at very high sensitivities from effects like gravitational lensing. Okay, so here's a neat model that you can consider. So in the standard picture, the dominant perturbations that see the CMB anisotrophies are adiabatic. So what happens is all of the components of the universe fluctuate at the same time, up or down. And the local curvature of space-time fluctuates in the opposite direction. And those are believed to be the dominant source of perturbations in the early universe. There's another type of perturbation, isocurvature, in which so you have fluctuations in one or more of the species that are compensated by fluctuations in another. So the overall matter density, the overall energy density doesn't fluctuate, but just the relative constituents at each point in the universe vary. And currently, isocurvature perturbations, for example, between dark matter and other components, are constrained to be less than 15% of the total But there's one mode of isocurvature perturbations in particular that's not very well constrained. And that is called a compensated isocurvature perturbation. It happens if you have a fluctuation in the baryon density that's exactly canceled by a corresponding fluctuation down in the dark matter density. So what happens is, suppose you had these isocurvature perturbations that are compensated. The overall dynamics of the universe aren't really affected. But if you look at different positions on the sky, you could imagine at this position you have fewer baryons. So the plasma is less baryon loaded. Diffusion happens on a larger scale, and the peaks shift around a little bit. You could look at another patch where you had more baryons. Diffusion gets pushed to higher scales. The peaks shift, but in the opposite direction. So you could construct an estimator for the isocurvature perturbations by basically looking not at the power spectrum of the entire CMB map, but at it in little patches and looking for this change in the shape. So you can do that with the WMAP data, and you get this map. This is a map of the baryon versus dark matter anti-correlation. So if you saw large hot or cold spots in this map of this delta parameter, which gives the magnitude of the isocurvature mode, you would be seeing that in that patch of the sky, it looks as though baryons don't trace dark matter, right? They're anti-correlated. Fortunately, this map is consistent with noise. So here's the power spectrum of this constraint using several of the WMAP bands. You can see that for each of the modes in this map, which is this QVW plot in the lower right-hand corner, we're sort of consistent with delta being 0. That is to say, the noise on the delta measurement that you get because of cosmic variance in different portions of the sky is consistent with this map of delta there.
So, can you say again how to do the map?
Exactly how you do it?
Yeah.
Okay, so you take the CMB map, you basically do a matched filter for the difference between the red and white curves here. And then you square it.
And the error bars, so that's the next part is just the power spectrum, right?
The power spectrum of that
And the
map
error bars
are from simulation. So you take, so most of the noise for this measurement is the sample variance of the scanning fluctuations. Because you're looking at the square of the map. And so if you look on the largest scales here, at L of 1, you're looking for a dipole distribution of the baryon dark matter anti-correlation on the sky. With this measurement, you're making about a 10% constraint, which is competitive with the sort of constraint that you get from other probes like clusters. Another thing that we can look for is cosmic birefringence. So if the CMB radiation is polarized, and as it propagates to us from the last scattering surface, you could imagine that if the universe were birefringent, that polarization angle will rotate as the radiation comes to you. And because the CMB is the furthest possible source that you can look at, even if you had a very small birefringence, the cumulative effect over cosmic distances would make it the best way to look for it.
Define birefringence.
So the left and right components of the linearly polarized light rotate at different speeds, or so you propagate at different speeds. So if you have light that's polarized in vertical direction, as it travels towards you, it will slowly rotate around. In a crystal. So you could model this as this exponential factor with this alpha as a function of n hat, which is giving you sort of a rotation angle for each point on the sky. So if the universe were a crystal, alpha would be a constant. But if there were different birefringence in different directions on the sky, alpha can be a function of n. And you can concoct models in which this happens.
Can you give an example of a concocted model?
Believably, or?
Well, what people choose to be the poster child for birefringence.
Yeah, so the one which Vera usually talks about is a Chern-Simons term in electromagnetism. But my understanding of that is at the level where I don't know whether it's pronounced Chern-Simons or Chern-Simmons. So you'd probably have to ask for some more detail.
It's science.
I better shut up before I say something else. So the best way to look for birefringence in something like the WMAP data turns out to be these correlations that we expect in the standard picture between temperature and this E-mode polarization. So if you have the polarization field on the sky, you can decompose it into two modes, E mode and D mode, which are real fields. And the E mode sort of comes into its peaks and troughs as a polarization pattern which is either radial or tangential, whereas the D modes tend to curl around off the full spot. And in the standard picture, there's a correlation between temperature and E modes. So if you stack all of the hot spots or all of the cold spots in the CMB, which actually correspond to overdensities in the early universe, you get a plot like this. So there's a central peak or central trough, and then BAO feature off its center. And so if you're sitting on this feature here, photons are flowing in towards the center. So you have a convergence of radiation, and that couples to polarization through Thomson scattering, and you get these radial polarization vectors around your peak. And as you get closer, photons are starting to flow out again, and you also get aligned polarization vectors, but now they're sorry, these are tangential, and now they're aligned radially as you get closer to the peak. And this is an E mode. So if you take your CMB map and temperature and polarization, you decompose it into T, E, and D modes, and you take the cross spectrum between T and E, you expect to see this red solid curve, which is just a harmonic space representation of this correlation in real space. So you can imagine if the universe were birefringent, if that birefringence were constant everywhere, you would just rotate E modes into B modes, because you're taking something which is aligned sort of at 90 or 0 degrees with these concentric circles and rotating them by 45 degrees, so now they're spiraling around instead of having this E direction. And another thing you could do is you could suppose that so if alpha varies as a function of position on the sky, instead of rotating E into D, that's just going to wash the TE correlation out everywhere. So you're just going to smooth this spectrum out. So the data points here are from WMAP. They're black points. And you can see that because they do trace the expected T correlation, you can put an overall constraint on the RMS fluctuation of the birefringence of sort of 10 degrees. The other thing that you can do is the same as with the compensated isocurvature perturbations. You can go to different patches of the sky, and you can look at the local TE power spectrum, the local TB power spectrum. And if you see something in TB which looks like what you expected to see in TE, then you take that as evidence of a rotation in the last scattering surface. So you can make, again, a map of this alpha band over the sky. Also in this case, it's consistent with noise, right? So you probably expected. It starts to get more interesting if you remove that factor of I in this rotation. So now you're just looking at something which is modulating the fluctuations at different points on the sky, rather than rotating the polarization. And that also leads to leakage between E and B. And you can constrain it using the WMAP data. It also affects temperature, because you're basically changing the amplitude of the power spectrum at different positions on the sky. And you can sort of construct a model of reionization, where you have bubbles of some radius and an amplitude. And in this amplitude radius plane, you can start to place constraints on reionization history. And WMAP is not got noise that's low enough to tell you anything interesting. But as you start to get to Planck noise levels, and then a next generation experiment, you can sort of dig into reasonable models of reionization, at least in this simple model. So that's sort of a picture of where the future would be. And it segues nicely into the second part of this talk, which is about using the CMB as a backlight. So you again have this nice fact that because the CMB travels to us from the furthest possible distance, it propagates through everything in the observable universe. And there are some effects which start to crop up at current resolution and noise levels, which you can use to probe astrophysics. So Graham talked a bit about the thermal and kinetic SE fluctuations. And I'm going to focus for the rest of this talk on gravitational lensing. So lensing is something that's only in the last few years become significantly detectable from the CMB alone. This lensing of the CMB at least. And with the release of Planck and the full SPT data set in a couple of months, it's starting to enter the regime of precision cosmology. So the effect is described as this remapping. So basically, rather than observing the primordial fluctuations, we observe them displaced by the gradient of this lensing potential, which is the usual thing from galaxy lensing, right? It's an integral over the matter or the gravitational potential with a geometry factor. And the only difference here is that the integral goes from redshift 0 all the way back to the last scattering surface. So there's a fixed source plane, the position of which we know really well. So this is a 10 by 10 degree patch of the sky. If you take the gradient of this lensing potential and then its absolute value, that sort of gives you a feeling for what the magnitude of the effect looks like at different positions on the sky. Now if you take an unlensed temperature map, and then you lens it with the potential from the previous slide, this is the difference that you get. So there's this little hamster dance between the two of them, which is correlated with these deflection vectors. And you can't really tell by eye, but this lens map is detectively non-Gaussian. So the lensing potential has perturbed the statistics of the CMB to the point where you can actually detect the lensing. I'll talk about that in a second. First, just some order of magnitude discussions of lensing. So this lensing potential is itself mostly a Gaussian random field. If you take its power spectrum as sort of a peak around 2 degree scales, which corresponds to the peak of the matter power spectrum, about halfway to the last scattering surface. So you have lenses that are about 2 degrees in size, but the deflections are much smaller. They're only about 2 1/4 or 2.5 arc minutes. The CMB lensing potential is mostly very large scale structures, so it's all linear. Okay. And it's only as you get up to higher multiples that nonlinear effects start to kick in. So you can use this part of the spectrum to constrain parameters without really worrying about modeling the nonlinear part. The effect of lensing does affect the power spectrum. It sort of blurs the acoustic peaks. But that only gives you one piece of information, which is kind of like the RMS lensing deflection. What you'd really like to know is what the lensing looks like as a function of scale. You'd like to reconstruct the lenses themselves. So here's the idea. It's similar to the estimators from the first part of the talk. And there's a nice connection to galaxy lensing, right? So if you decompose the lensing potential into convergence and shear modes, in galaxy lensing, the shear modes you can sort of measure by assuming that galaxies are randomly oriented. So you measure the orientation of a large number of galaxies, average to beat down the shape noise. You get a measure of shear, and then you can back it out to measure the phi or the gravitational potential. In the CMB, the situation is even easier because we know the distribution of these hot and cold spots from the power spectrum. So we get magnification and shear kind of at the same time. So if you just consider the magnification effect, right? You're either shrinking or enlarging patches of the sky. That's just going to shift the power spectrum. It's like a local change of scale. You expanded or shrunk the x-axis of this plot. So again, you just look different positions on the sky for this effect, this difference in the power spectrum. And you can reconstruct that. You can use that to reconstruct the convergence. And then the shear is exactly the same thing, except now instead of looking for a shift in this x-axis that's the same in any direction as the point on the sky, you're looking for a shift where the axis grows in one direction and shrinks in another direction. So you're taking the difference between the power spectrum in two directions. And you can apply this to a CMB map, and you can reconstruct maps of the lensing potential. So this is from Alex Van Engelen in SBT. We've got a lens simulation. Here's the reconstruction with blobs in it. An unlensed simulation, which does not have blobs because we've reconstructed noise. So this is the noise level of your lensing estimate. And then this is what you get when you actually look at the data. And these two things are consistent. So these blue blobs here are large structures along the line of sight. We've integrated with contributions all the way from ourselves to the last scattering surface, but with a peak around redshift of 2. You can take the power spectrum of this map and compare it to your expectations, and you have a good agreement with lambda CDM. The detections from action SPT are at sort of 4 to 7 sigma significance, so even particle physicists would believe them. Planck is coming along on March 21st and is really going to step this up a notch. So I can't talk about Planck yet, but I can use forecasts to talk about the sort of thing that we should be able to see with Planck. It's important to note that all of the forecasts here are based on published noise levels and do not involve any real data. It's important to note, especially because I'm being recorded. So again, you have with galaxy lensing shape noise from the finite number of objects that you can observe, and with CMB lensing shape noise from the finite number of CMB modes that you can observe. So high resolution experiments like ACT and SBT have lower noise levels than Planck. But because Planck measures the full sky, the statistics are better. So if you're trying to measure something like the power spectrum, at Planck noise levels, these little black boxes are the constraints that you could expect to get. You can make a map of the lensing potential. Because the noise is higher, it's not going to be as impressive as the SBT map. But if you blink between reconstructed map and then input, you see correlated features. So this is kind of like the Kobe map of the lensing potential. I'm almost out of time. Okay. So I'll skip the end then. I just wanted to say that most of the new things that we can learn from the CMB are not going to come from the power spectrum, which is more useful just for nailing down the parameters. There are lots of probes that you can imagine for new physics. And they're also related to probes that you would use to study astrophysics. You get both of them at the same time. And in particular, every high-resolution CMB experiment is now a lensing survey in disguise.
Maybe one quick question before we move on to the next speaker. Okay.
So, how competitive are Planck lensing measurements forecast to be compared to low redshift probes of structure, like clusters, that sort of thing, on sigma rates or those kinds of parameters?
Okay, so for Planck, you would forecast a sort of 20 to 30 sigma detection of the lensing potential.
Yeah.
So if you said, what is my corresponding constraint on sigma 8, that would be 2.5% to something lower.
So competitive with current cluster and that sort of thing.
Okay, let's thank the speaker again. Our next speaker, as he says, our next speaker is Johannsen. He did his PhD at the University of Arizona, and he is now a CITA National Fellow at the University of Waterloo, and he's also a postdoctoral fellow at the Broadened Institute. And his research interests include black holes, gravitation, and relativistic astrophysics. Wait for him to say, and we can begin.
Okay, thank you very much. In this talk, I'm going to show you how we can test one of the most fundamental properties of black holes, the Noether theorem, with observations in the electromagnetic spectrum. General relativity, our current theory of gravity, as you know, has been very well tested, both in the solar system and with double neutron stars. However, in the strong field regime that we find around compact objects and black holes in particular, general relativity still stands practically untested today. And so this is a very important question that we want to address. And in this talk, I'm going to show you how we can do this observationally, and I'm going to show you the current constraints that we get from the data that we have available at this point. And in this endeavor, it's a pleasure to mention some of my collaborators who all have contributed at some level to the results that I'm going to show you in this talk. So the Noether theorem tells us that a black hole is described by only two parameters, its mass and its spin. And that's it. If you have a star that collapses and forms a black hole, during that process you can show that at least for small, in a certain setup, that any other signature other than mass and spin is radiated away as gravitational waves. So this means there is a proposed mechanism which can actually form black holes in nature. And so the expectation is that all the astrophysical black holes that we observe are Kerr black holes. And the Kerr metric is our way of describing black holes. That is the way it is done. How about now if you think about this a little? You have a star. The star explodes in a supernova, collapses. It forms a black hole, and at the end of that process, you have an object which you can describe with only 2 parameters. That's indeed very remarkable. And it doesn't have to be this way. First of all, as I said, general relativity still stands untested for the most part in the strong field regime. And there are a number of alternatives. You can have a different kind of black hole. You can have a different kind of object, or even things that we don't really know about. Finally, you can have some kind of stellar configuration. So this is something that we want to do, and I want to do this observationally. And the question that I'm asking is it a Kerr black hole, or is it something else? And here's the recipe. This is the way to do it. You take the space-time of a black hole, and you expand it in multiple moments. This is an analogy to what we all know from, say, Newtonian mechanics or electromagnetism, where you have, say, a charge distribution, and you want to know what does your electric potential look like at some distance from the source. Then you can expand your charge distribution in multiple moments in spherical harmonics, and you characterize the electric potential in terms of multiple moments. Turns out you can do this for a black hole as well, only in this case it's a lot more complicated, because space-time is curved. But you can do it, and it turns out that the mass is the first moment, the spin is the second, and for a Kerr black hole, that's already the entire story, because all higher order moments are completely determined in terms of those 2. So the strategy is, let's take, say, the next order moment, the quadrupole moment, which for a Kerr black hole is simply minus the spin squared, modulus some vector of the mass. And then I add this parameter epsilon here, which is dimensionless. And then I can calculate observables and use observations to see whether my quadrupole moment really is minus the spin squared. In other words, whether epsilon is really equal to 0 or not. If epsilon is equal to 0, then we know that we have a Kerr black hole. If epsilon is not 0, then there are 2 possibilities. If we assume general relativity as the underlying theory, then we know that the object cannot be a black hole, simply because a Kerr black hole is the only one in general relativity. If, on the other hand, we know that the object is a black hole, for example, if we observe an event horizon, then we know that the Theorem does not hold, and general relativity is not our theory in the strong field regime. Now, this approach has been largely developed in the gravitational wave community, starting already in the mid-90s. What I'm doing, I'm using this approach in the electromagnetic spectrum, and then calculate observables and compare it with the data that we have available. Originally, I've been using a metric which allows me to do this for small to intermediate values of the spin. However, for astrophysical black holes, that was a real limitation because many of the black holes that we know about seem to have a spin which is very high. So it was necessary to develop a framework that allows me to carry out tests really for all values of the spin. And this is what I did. I systematically constructed a metric which allows me to probe black holes all across the spin spectrum for arbitrary values of the spin, and then see if we find any potential deviations from that observationally. Just to give you an idea what this looks like, this is the metric that I designed. You may recognize this as the Kerr metric, where this function h shows up at certain very specific places, and this function h includes this parameter epsilon 3, which is my deviation parameter that I can use to study potential deviations from the Kerr metric. Okay. So now let's build a little intuition. What happens if you change the quadrupole moment of a black hole? And there are a couple of things. First of all, there's a shift in the location of the ISCO. The ISCO is the innermost stable circular orbit. If you have a black hole, you can only sustain a matter particle on a circular orbit up to a certain radius. Inside of that orbit, it will just plunge because there is no longer any stable circular orbit. Many times this is taken to be the inner edge of an accretion disk, so this is of great importance for astrophysical black holes. And here what I'm plotting is contours of ISCO radius in units of the mass of the black hole. There's a function of spin and this deviation parameter. The dashed line is what you have for a Kerr black hole. But what you can see is as you change this deviation parameter, the location of the ISCO can be significantly different. Yes?
This how to design the method, is that determined once you have this small computation?
So the way I designed this metric is you You start with a metric that has no spin at all, Schwarzschild-like metric. Well, actually, you take the Schwarzschild metric. And then what we do is in the TT and the RR component, you introduce an expansion in 1/radius, which includes a whole host of different deviations parameters. And this epsilon 3, that's where this number comes from, is the lowest order term that is not ruled out by solar system tests. So you introduce an expansion 1/r in the Schwarzschild metric. Then you use a complex coordinate transformation. Now we're getting fancy here. So you take Schwarzschild, you get complex coordinate transformation, which in the end introduces the spin in your metric. This is a way that was designed by Newman and Johannsen in the 1960s. They found that if you take the Schwarzschild metric, you can rotate that into the Kerr metric if you have a complex coordinate transformation. And this is the same idea. I take a modified Schwarzschild metric, and this is not the only way of doing it, but this turns out to be the way that works very well for what I'm doing. And then you rotate that in the Kerr-like metric, which includes the Kerr case if epsilon is 0. And otherwise you have this metric that I can use for the purposes that I'm interested in.
But what this is saying is that in total, the solution space, if it's point mass solution of general relativity, you're saying that the gravitational field of the point mass is not spherically symmetric. It sounds like a dangerous thing.
That is,
but there's some spontaneous breaking.
That is, but that already doesn't work if you go from Schwarzschild to Kerr, because Kerr already has one forward.
Well, if you add in spin first, then
yes,
break rotations.
That's right. So that's what we do. Okay. So
does this metric satisfy some basic constraints of symmetry and asymmetry and so on?
yes. Oh, this is okay.
So there's obviously a limited class of models
Well, actually,
based on metric models and very specific type of tweaking that metric.
that's right. So there are two. The main idea is the Kerr metric is very specific and special properties, and I want to construct a metric which retains as many of those properties as possible. So in this case, my metric is stationary, axisymmetric, asymptotically flat, vacuum, not in general relativity, but in some more generalized theory. And in that way, what I construct is a metric which, outside of, say, event horizon, it's not really that, but that's the idea. Outside of that, my metric is completely regular everywhere. So in other words, I have a framework where I can put an accretion disk, and I can study deviations from the relativity arising from this accretion disk wherever I put it in my space-time. That's the key property that I need.
I still don't understand. Usually people do the PPM formula.
That's right.
You do expansion,
That's right.
and then GR predicts very specific coefficients of the corrections. Then you measure different corrections, and you compare if they all agree.
That's right.
And if you have a different theory, those corrections may be different. But this is all, you start with Newtonian, and then you do the post-Newtonian.
That's right. But
Here
it's different. The key point is that post-Newtonian PPN only works in the weak field regime, because now we're in the strong field regime. And what PPN lives on a Minkowski space where you just modify the next order.
But the sources can be in a strong regime, even though
That's
no
right.
expansion.
But
the coefficients of your expansion will depend on the property of the source.
that's right. But you only calculate observables that are far away. In this case, what I have to do, I have to modify accretion disks, or calculate accretion disks. So I really need the proper modeling of the space-time right outside of my central object. That is why I cannot use a PPN expansion. I have to modify the actual metric in this way. I suggest let's maybe
You do a integration theory around class space. You do a integration theory around a solution to an extension.
That's right. I would like to let's maybe hold your question. Let's maybe talk about that after during coffee or so, because I want to get to the results, because there's very interesting stuff that is coming along here. Okay, so I showed you that the ISCO experiences a shift in the space-time. Another one is the light bending. So now we have a black hole which is rotating counterclockwise. We are looking at it in the equatorial plane. And suppose you have a bunch of photons coming in from the right here. Now, depending on this value of this epsilon parameter, you see that the scattering that the photons experience can be significantly different. And there is a similar shift that you observe in the photon frequency. So by the end of the day, what this means, you set up your detector. Depending on the value of this parameter epsilon, you will see a different set of photons for the different spectrum. And that is what I'm looking. Okay, so now let's talk about targets. The first one, of course, is Sagittarius star, the supermassive black hole at the center of our galaxy. Here what I'm plotting is essentially the size of the black hole as seen in the sky as a function of distance. And you can see that Sagittarius star is the largest as well as the closest. In size, it's closely followed by M87, which is a very far, or relatively far away, but a lot more massive than Sagittarius star. So in the sky, it has almost the same size as the one in our own galaxy. And then this is only for supermassive black holes. There are others that are relatively in the same size. So this is something that we are interested in, and this brings me to my first application. We want to image this shadow of a supermassive black hole, and in this case primarily of the galactic center M87. So the way that you can imagine this, you have a black hole, and you put an accretion flow around it. Because of the light bending, well, photons are emitted from the accretion flow. Because of the light bending, they will bend around the black hole and actually make it into your detector, so you can look behind the black hole. Now, however, if these photons approach the black hole very closely, they are captured. So if you take an image of this, there's literally going to be a black hole in the middle. And this is what this looks like. This is one particular accretion disk model. Here what we did is we took my formalism and we plugged this into a code that was already developed by Broadened. And we generated images of this modified space-time where you study these images as a function of this deviation parameter. And here I'm showing you images for two cases, two different values of epsilon. Now it has been known that for some time that the shadow, which is this part here, the shape of this shadow depends uniquely on the mass, the spin, and the inclination angle of your accretion disk. And what I showed is that this is also uniquely true for the quadrupole moment, or any kind of deviation that you introduce in this way. What happens if you change the quadrupole moment, the shape of your shadow either gets more oblate or more prolate relative to the threshold. Now if you look at this, you might say that, well, yeah, that's wonderful, but these images actually don't look that different. So what does that imply? But the good news is that observationally we actually are in a position where we can tell the difference between these images. So this is very exciting. So let me get to that. There has been the observations that we have done. You do this with very long baseline interferometry. You couple several radio millimeter telescopes in one global array. And what has been done in two big observing runs is JCMT, Karma, and the SMT. And then you use those data and you fit them to the accretion disk models that I just showed you. And this is the results that we get. So here what I'm showing you is the inclination angle of the accretion disk as compared to this deviation parameter epsilon. And what you can see is you have an inclination angle of somewhere around 60 degrees, which is exactly the same that people had in the previous analysis, which they did for curve black hole. In other words, this deviation parameter does not change the inferred disk inclination angle. That is a good sanity check because it showed this deviation parameter is going to affect the spin, but not the disk inclination. But you can already see here that the non-zero value of epsilon is favored over a zero value. Now I can also look at the position angle of the spin in the sky, again versus epsilon, and you can see that you have two solutions generated at 180 degrees because you don't know whether it's pointing this way or this way. But what you see here is that this does not depend on epsilon at all. Again, for the reasons because that does not affect the position angle. But again, you see that a positive value is slightly favored over a non-zero value, over a zero value.
You haven't said anything about the emission model.
Yes, so it's a RIAF model. RIAF means that you have an accretion flow model which is essentially in the spherical symmetric potential. Then you make an assumption. You have two populations. You have thermal electrons. You have non-thermal electrons, and you make an assumption for the exact composition of that, which you fit to observational constraints that you get, say, from polarization measurements. So you fix some of the coefficients in your model based on observations that have been done so far.
There must be some generosity in your derived epsilon parameter and what you take for your emitting
For the model.
emission structure.
For the emission structure. So
You don't really know what the bias vector is.
That's right. So that's actually the key point. There are 2 points to the answer that I would give you. The first one is, right now we are doing detailed simulations of that, where we investigate what exactly is the effect of the accretion flow on this deviation parameter. The sensitivity that we expect is great, and I'm going to talk about this in just a moment. So that we just, that the hope is that, well, let's see, we are quite optimistic that we're actually able to tell the difference between that. Okay. Now, this here is the very interesting part, because now I have epsilon, this deviation, versus this spin. And now you can see that, wow, now there is something going on here. You see that non-zero value epsilon with the current data is marginally favored over a zero value epsilon, which you would have for a current black hole. Now, this is only a slight difference with the current data. However, as more data become available, we are really able to condense these contours down to some very precise levels. And the way we want to do this is, of course, with the Event Horizon Telescope. This is a global array of radio and sub-millimeter telescopes. The key proponents of this array are going to be ALMA. And the very interesting one is the SPT, which will allow us to achieve very long baselines, giving us absolutely superb resolution. And this is an endeavor which is coming, which is making great progress, and this is going to happen within the next couple of years. So this is very exciting. Okay, now there's one additional feature that we're interested in. Here, what I'm showing you again is the shadow of the black hole, and what you see is that surrounding this shadow is a bright and narrow ring. This ring is only determined by the geometry of the spacetime. It's not affected by the flow properties. This essentially corresponds to the projection of the circular photon orbit into the image plane of the observer sky. And what you see here, this is for a current black hole. I hold all parameters fixed, and I only change the spin of the black hole. What you can see here is two things. First of all, the diameter of this ring does not change. The diameter of the ring is only determined by the mass, and the mass of the system provides the size of it. So in other words, if I measure the diameter of this ring, I infer the mass of the black hole. What you also see is that the shape of this ring remains nearly circular as long as you have a curved black hole. However, if we now change this epsilon parameter, then you see that the shape of this ring becomes asymmetric. And this is something that you cannot produce with a curved black hole. This is clearly different. This would be a smoking gun for a violation of the Noether theorem. And I can also make this quantitative. If I plot diameter as a function of spin or any other parameter as constant, it's only determined by the mass. I can plot the displacement, what you saw in the image plane, as a function of spin. That will give me the spin. I can plot the asymmetry of the ring as a function of epsilon times some function of the angle. So that gives me a way of directly measuring the quadrupole and seeing a smoking gun deviation if it exists from the curve metric. Okay, one thing that I did, for maybe this kind of array, including ALMA, the SPT, I simulated a mass measurement, or results for a mass measurement that you would get with this kind of setup. So you can measure the mass and the distance of the galactic center black hole by observing stars orbiting around it. You observe the orbit of the star, and then from Kepler's law, you can infer the mass, the central mass. And people have done this with great precision, and this black line here, this is the 2 sigma contour that you get from the stellar orbit measurements. And what I did, I combined this, using this as my prior, combining this with the mass measurement from the diameter of this ring. And the contours that I'm showing you here is the 1 and 2 sigma contours for this kind of array that is going to happen. So you see that the improvement is going to be significant. And this is only for the mass measurement, so this is something which is going to be very interesting. Okay, now I want to shift gears a little bit. Now we talk about relativistically long ion lines, so now we shift from the radio to the high energy spectrum. This is something that you can observe both in AGN and in galactic black holes. So here the picture is you have an accretion disk, there's iron in your accretion disk. Temperatures are such that iron still retains a couple of electrons. This iron is then hit by some very energetic photon from some corona or somewhere, and it knocks out the electron to the ground state. And then all the other electrons will recombine, emitting at very characteristic energies. In this case, it shows up at primarily 6.4 keV in its restaurant. Now, instead of observing some Lorentzian profile, you see a broadened profile, which is produced by all the relativistic effects. And what I simulated here is profiles of this ion line. This is flux versus energy, and what for several values of my epsilon parameter. You can see that the line profiles can be clearly different if you change this epsilon profile, providing yet another probe of having access to this epsilon parameter by observing these ion lines. And I estimated the precision that is going to be required by current on future X-ray missions in order, what it would take to detect these kinds of deviations. Again, this is deviation here and spin over here, and I just plot the difference in percent of a given ion line, a fixed spin to another. And what you can see is that the greatest precision is going to be achieved for black holes with a high spin. But what you can also see is that for some moderate inclination angle, if you have a mission which achieves a precision of, say, 5%, you're able to constrain this deviation parameter to order unity, irrespective of the value of the spin. So this could be a very nice probe. Finally, this is something that I'm working on right now. This is one black hole in particular. This is a galactic black hole, J1550. This black hole has the very interesting property in that it combines all the possible probes that we have in the high energy spectrum at this point. So you can model the accretion disk spectrum of a black hole. And this black hole also has an ion line. Combining those two, people have measured the spin of this black hole if you assume general relativity. And what I'm doing here is I'm using that measurement as my prior, and I combine this with another measurement that has been obtained for this black hole. You observe quasi-periodic variability. Quasi-periodic variability means that you have emission at characteristic frequencies which is thought to originate from modes that you can excite in your accretion flow. At this point, the model of this is very uncertain, and there are a lot of open questions. But what I'm doing here, I'm combining those models with the existing spin measurements for two different models, obtaining the best case constraints from this black hole that we have at this time. And this is what you have. This is the 1 and 2 sigma contours that you observe, that you get. And this is not a simulation. This is current data. And the only open question here is how can you tell the difference between these models? And the detail of that is not so critical right now. This is two different models. At the moment, there's no way of telling the difference between these two models because observationally we simply cannot do that. But the solution to that is called LOFT, the Large Observatory for X-ray Timing. LOFT is 1 out of 5 proposed missions to be selected for ESA's next medium-sized space mission. LOFT has an absolutely spectacular collecting area exceeding 10 square meters. And in this plot, this is collecting area as a function of energy compared to all the other X-ray missions. Well, not all of them are very critical ones, including the one IXO Athena that was proposed, which is substantially smaller in collecting area than LOFT. In other words, LOFT is going to have absolutely precise measurements of the timing properties, so you can observe stuff orbiting around a black hole in real time. We're talking about microsecond resolution, just because we have this enormous collecting area, as well as the correct receivers that we need for this. Now, with this instrument, we are actually able to tell the difference between these QPO models, these models that I just briefly mentioned. And simply that is with current instruments, we're able to detect only, well, we are only able to detect maybe 1 or 2. With the LOFT, we're able to detect high order harmonics And with that, we're able to tell the difference between these models because these models make different predictions for higher order harmonics. So in other words, with that, we're in a position where we can really tell the difference, and then we can get to the constraints that I just showed you. Okay. So then we wrap this up. In this talk, I showed you a framework which I can use to test the LOFT theorem, which is a property of black holes in a regime which is practically untested today. And I showed you a way of how we can do this, and I showed you several different observables and ways how we can probe this observationally. One of them is the imaging of the galactic center black hole as well as M87, potentially others. I showed you fluorescent ion lines, and I showed you variability, which we may assume observe with LOFT, and I showed you the constraints that we have for the current data, and as future data becomes available, especially for the event horizon telescope, this is something which is very interesting, and we are going to be able to get real good constraints on potential deviations from the way it works. Thank you.
For the angle, inclined angle that you mentioned in the talk, is that the inclined angle between the accretion disk and black hole?
No, you assume, in this case, you assume that's the same. It's the inclination angle with respect to the observer. So you have your accretion disk, and it makes a difference whether you look at it edge on or face on. So that's the inclination angle.
Okay. But there is some like other models we discussed when the material is going into the black hole, if there is any inclined angle of it, then you
That's
do
right.
some actual turbulence.
That is actually a very recent investigation that people have been doing. There's the first GRMHD simulation for this kind of effect, which came out just 2 months ago. People have been looking at that for galactic black holes where you have, say, a thin accretion disk. We have been looking at for maybe a few years. So this is something that you want to probe observationally, but it's still a pretty young field.
So the black hole is a persistent particle. There's no reason that should align with the angular momentum particle. Now, if you gain angular momentum gradually, then the gravitational radiation will remove the misaligned component of the persistent particle. But you then apply this, well, if you neutron stars should then also have large persistent particles if you're modifying them.
And they do. And they do, and in fact...
Well, wait a minute. You're talking about persistent particles, what, 0.5? So they would spin down dramatically fast. There'd be huge spin-orbit interactions, or particle-orbit interactions, in binary neutron stars, right? Nothing like that is seen.
So, several points. First of all, for neutron stars, the quadrupole moments are a lot smaller, because we observe spin frequencies to maybe 1,000 hertz, roughly. And the quadrupole deviations that you see are a lot smaller than what you would have for a curve level. For a quadrupole moment, for a neutron star, the quadrupole moment always depends on the spin. In this case, my quadrupole moment is a free parameter.
Wait. If they're modifying Einstein gravity, you give a black hole a persistent particle moment.
That's right.
Surely neutron stars also have a persistent particle moment. I can see how, as you increase the scale of the object compared with the gravitational radius, you might get some suppression, but the neutron star is hardly bigger.
That's right, but at the relevant spin frequencies, that is still what we would get. Now, at a practical level, my thesis advisor actually gave this kind of project for neutron stars to his new graduate student. So he's using my framework to investigate that. But the results that they have so far is that, first of all, observationally at this point, it has not been possible to really probe this. But what you see is...
I don't believe that. Yeah, I don't believe that. At the level you're talking about, I don't believe that at all.
Yeah. 10 to the minus 5, we can test the neutron star GR. The level of 10 to the minus 5.
10 to the minus 5. We might be talking about different things. 10 to the minus 5 and what?
Some parameters. Anyway, yeah. It's extremely sensitive.
So what I'm talking about is you can calculate pulse profiles that are emitted from neutron stars, for example. The shape of these pulse profiles, what people have been using so far, they only use the Kerr metric. They either use the Kerr metric to model these pulse profiles, or they took the Schwarzschild metric, where they introduced spin-dependent effects as corrections. And for the first time, what people are doing now for neutron stars is to introduce quadrupole corrections in this manner to model these pulse profiles.
This isn't the main thing. I mean, if the star has a persistent quadrupole, there's no reason to expect it to align with the spin. And so it will be a persistent, it'll be a quadratic source of gravity waves, right? The metric will modulate it by
that is different. That's a different setup. So in this case, we always assume that the quadrupole moment. So we only.
Well, in the black hole case, there's a reason to imagine that might happen because you're gradually, say, adding spin to black hole by accretion or by discrete stellar interactions. But in the neutron star case, it happens, and then you have in your theory some spontaneous integrating, which gives some randomly oriented particle, I guess.
So in that scenario, that's right. You have gravitational radiation, and it eventually settles down to some stationary solution, right? And with the point where this kicks in is if you have a stationary setup, because I'm not modeling dynamic spacetimes. I'm considering stationary solutions, which in this case you would have if the quadrupole moment is aligned properly, and I study deviations from that as well.
The Shapiro delay, what did you do?
Yes.
So very cutting tests is stars.
That is true.
Well, you should talk to him afterward because he's the biggest expert on double transfers, double pulsing systems.
Yeah, let's talk about that because there are some very subtle nuances. But yeah, let's talk about that.
I know there are more questions, but we're out of time. So I think if you have more questions, you can ask the speaker afterwards because we have